recording started. And let me now share my screen. Here we are. Let me start also my Teams on the phone so I can check what you see. 1 second. Okay. Good. And now let me go to the relevant web page. So this is the usual web page of our tutorials. And the lecture that we introduced last time is, sorry, don't send. The lecture that we introduced last time is Sustainable Management of Water Resources. I click on it and I go at the end. The end is here. Okay, so last time we got somewhere here, reducing the impact of extremes, and we already discussed this. So let's go down to water resources assessment. So far, we discussed about sustainability. We defined what sustainability is, and we also discussed how much water is available at the global level over the Earth, and we discussed some issues, some sustainability issues related to water. Now we have to go into more details. Of course, when we have sustainability issues related to water, it means that there is a problem in water resources availability. And usually there is a mismatch between supply and demand. And then the problem arises to optimize the management of water. And a relevant question, a relevant preliminary question is how much water is there? How much water is available in the water source that we are planning to use? And it seems like a trivial question because, you know, any time that you make a budget, any time that you try to optimize a resource, of course, it's clear that you have to start on the estimation of how much resource you have in your bank. In this case, we are talking about a water bank. And it seems like it's very easy to do that because we are used to think at aqueducts that usually take water from a reservoir. So it looks quite easy to estimate how much water is in the reservoir. And when we refer to our home or to our city, usually we refer to a tank, an upstream tank in the water supply system, which is, just 1 second, I want to take the chat into my screen. So let me put it in the second screen. Very good. And as I said, usually there is a tank upstream, a water supply system, and you know the size of the tank, and then it looks like a trivial question to estimate how much water is into it. Actually, when we refer to the environment, when we refer to the natural environment, usually we take water from lakes, we take water from rivers, we take water from aquifers, and then the question becomes more complicated. The question related to how much water is there becomes more complicated. And this is what we want to discuss. We want to discuss, sorry, because there is a waiting room still, and I need to get some students in. 1 second. Okay, very good. So, in the natural environment, it's more complicated. Think of a river. It's not easy when you look at a river to understand, to estimate how much water is there. And this is what we are going to talk today. And, you know, what we do usually is to make observations and to make surveys. So we get an experience, we get knowledge through observation of how much water is there. And let me give you an example. If you have a natural reservoir like a lake, what you do is, in order to understand how much water is into the lake, what you do is to make a survey of the geometry of the lake. This is a way to get data that support your water resources assessment. So one possibility is to go through data. Just keep in mind that the example that I made of a lake is relatively easy. When you refer to a river, the geometry alone is not enough to estimate how much water is there, because the water in the river is flowing, which means that the faster the flow, the more the water you can take. This is obvious. It means that you have also to estimate the velocity. So these observations are quite complicated. They are not trivial. And if you think of an aquifer, observation is even more complicated. So sometimes observations alone does not suffice. Sometimes we don't have the opportunity, the capability to make observations because, they require efforts, they require resources, human and economic resources. So the moral of the story is that data alone often are not enough. And then what can we do? What we can do is to try to understand how much water is there through mathematical modeling. And therefore, just 1 second, waiting room again. And therefore, you have two options. Either you observe or either you build a mathematical model. These are the two options that we will discuss. And observations are quite easy to understand. The methods to pass from observations to the reply to the question, the methods to pass from the observation to the estimation of how much water is there are already a bit more complicated. But still, if you go through observation, is easier to understand. If you decide for mathematical modeling, of course, you understand this route is a bit more complicated. We need to understand how we can build a mathematical model of something that it's part of nature. Water can be flowing water. So we need to build a mathematical model that describes this entity, water, which may be fixed in space and time, or can change its position and its state in space and time. Because if water if water is moving, you need to describe this movement. So our task then, if we choose mathematical modeling, is to study a dynamical system. Dynamical because it's changing in space and time. Changing in space means that water is changing position. Changing in time means that water in the same position is changing some of its behaviors, which may be, for instance, velocity, which may be available volume. So we need to study this dynamical system. Dynamical means varying in space and time due to the effect of forcings. Now, what is a dynamical system? Let's focus on this page on the definition. A dynamical system defined as, read here, particle or ensemble of particles whose state varies over time, okay? And thus obeys differential equations involving time derivatives. This is the definition of the dynamical system. You may wonder why the description of a dynamical system requires the use of differential equations. And I want to tell you why, because of course differential equations are a bit of a complications. First of all, what are differential equations? Let's suppose that I have to describe a variable, which may be volume of water into a lake. It's a very simple variable related to water resources assessment. Again, let's think of a volume of water into a lake, okay? Sometimes I cannot directly write an explicit expression for the volume of water into the lake. And let me make an example through the graphic blackboard, because I think it is really important that we try to understand what we mean. Just 1 second, I am opening my graphic blackboard. 1 second, don't look at the screen now because I have to prepare it, and I don't like, let me just, okay, prepare everything. So, white color. Okay, I'm almost reading. Take my pen. Let me see if everything is working well. Not yet. 1 second. Okay. Let me see. Give me 1 second, students, and then I get it. For some reason, it doesn't work. So let me see. Yeah, I understand why. Sorry for that. I was trying to draw with a white pen over a white sheet, so of course it didn't work. Okay, and now let me share my screen and pass to the graphic blackboard. Okay, let me see on the chat if okay, everything is fine. Okay, 1 second. Here we are. Okay. Now you can see my blackboard, and I was saying, let's suppose that you have a lake, and let me design a cross section of a lake like this one. Okay, and let's suppose that you have a water level here, which is something here. Okay, this is water level into the lake, and let's suppose that we want to describe here the volume V of water into the lake. Okay, so one possibility to describe the volume, maybe we may think of an explicit equation, like for instance, I could write something like V is equal to a function of some inputs. Okay. Of course, if I want to write a function like this, I have to identify it, and which is not easy, because keep in mind that I want to describe V as a function of t, as a function of time. So one possibility to identify such a relationship may be, for instance, if I define the water level into the lake. So let's suppose that I identify with the water level into the lake with respect to a reference plane. Let's suppose that the reference plane is the lake bottom, and this is the water level H, depending on T. So one possibility could be, if I want to write this relationship, V as a function of T is expressed as a function of HT. Okay, this is one possibility in order to describe the water level, in order to describe the volume. And sometimes for some systems like a static lake, this may be possible. It's a description that may be possible. On the other hand, there is to say that in order to do this, you need a continuous measurement of the water level, and you may not be able to derive it. So in this case, if we don't have observations of the water level, we need to identify another equation. And in physics, very often, when we want to describe dynamical systems, we use conservation laws. Conservation laws. What is the reason why we use conservation laws? Because in Newtonian mechanics, in order to describe the movement of bodies, and water is a body, we can use Newtonian mechanics. And in Newtonian mechanics, which is a theory of physics, we can apply conservation of laws. And in particular, we can apply conservation of mass, and conservation of energy. Conservation of energy. This is what we do to describe water systems. When we describe water systems, and in particular flowing water, we need to apply these two conservation laws. And sometimes conservation of mass and conservation of energy, in many cases, allow us to completely describe the system. But conservation of mass, for instance, which is simpler than conservation of energy, can be expressed only through an equation that describes the change of volume. So look at our variable here. Our variable is the volume, V. Conservation of mass only describes the changes in the volume, not directly the volume. And when an equation describes changes, it's a differential equation. And let me make you an example. Suppose that for this lake, we don't have measurements of H, of the water level. So we apply conservation of mass. How can we write conservation of mass for a lake? Let me identify how the lake can be filled by water. And let's suppose that it can be filled only by rainfall, which we call PT. And then let's suppose that the only way water can get out from the lake is through evaporation, which I indicate with, EDT. Of course, this is just an assumption. We know that into a lake, we can get water also through rivers. But let's suppose that here, the only inflow into the lake is given by rainfall, and the only outflow is given by evaporation. And then I can write a differential equation, a conservation law, conservation of mass, in this way. I can write PT, which is inflow into the lake, minus ET, which is outflow. It's equal to the derivative with respect to time of the stored volume. You see that this is a differential equation because I am describing the changes in time of the volume, the changes in time. And what do I need to do from the changes, from the volume changes, to get back to the value of the volume? What I need to do is to make an integral of the changes in time over time. I need to make an integral of the changes. If I sum the changes, then I get the variable. This is integration. So you just have to keep in mind, and why I'm doing this premise. I'm doing this premise because I want to make you clear that sometimes you have to use mathematical models to plan water resources. What kind of mathematical models? In most of the cases, you will need to apply conservation laws. Conservation laws describe changes, and therefore they are differential equations. Differential equations for the variable of interest. And then you need to make an integral at the end of the story to get the value of the variable that allows you to plan water resources management. And I am making this premise because I want to be clear why we have to use the theory, apparently complicated theory of differential equations and integration to make water resources management. It's very simple. I have water that is moving. It's a dynamical system. I am repeating what I just said. It's a dynamical system. I need to describe it mathematically. I can use conservation laws. They are differential equation. I need to make an integral to get to the final tool, the variable that allows me to make the design. And the very reason why I make this premise is that I know that we engineers, we don't like terms like mathematical modeling, differential equations, integration, because we are technicians, not mathematicians. So in principle, very often we don't like spending too much time on the theory. But actually, these tools, mathematical modeling, differential equation, integration, are very simple to use. So we are overly concerned. We think that differential equation, integration are very difficult stuff. No, it's not difficult. I mean, a differential equation, what is the meaning? It describes changes instead of describing the true value. It describes changes. And then you need just to make a sum of the changes. Integration is a sum. The sum is the simplest operation that we learned to do at the primary school. So there is no reason why we learned it at the primary school and now after 20 years we are concerned by integration. It's just a sum. Okay, and now let me back to the previous screen. So 1 second, because I need to de-share this and share another one. So let me back here. Let me be back here. And once that we defined why we need mathematical modeling, why we need to study dynamical systems, now let me focus on the basic question, which is very technical. How much water is there and what is its quality? This is the question we have to reply. And as I said, we have two avenues, observations or mathematical modeling. Sometimes we need to integrate them. Remember, when we classify methods in engineering, you don't have to think about strictly separated boxes. Classifications are useful because you fix in your mind what are the possible tools. But very often you need to interpret classification as a flexible grouping. Okay, so it will happen very often that even if you have observations, you have to use mathematical models and you have to combine the two. And this is also needed for another reason. When dealing with water, as Leonardo said, you have to use your reasoning and you have to use your experience before the theory. And why that? Because water is difficult to describe and the description is subjected to uncertainty. This is something that you have to keep in mind. And when there is uncertainty, in engineering, let's say that you always have uncertainty. But when dealing with water, uncertainty is higher. We will understand why. And when you have uncertainty, you have to use all the information available. You cannot ignore some kind of information because you think that maybe it's too complicated to get that information, and therefore you rely only on a part of information which is the easier one to take. You can't take the luxury of ignoring some information, meaning that if you have observations and you have also the opportunity to use mathematical modeling to integrate the information that observations tell you, then you have to mix the two. You have to use everything that it may be useful for you. And again, how much water is there and what is its quality? This is our question. Look, as engineers, we always have, sorry, I am putting the blackboard back in its location. As an engineer, you always have to have in mind what is your question, okay? Okay, as I said, it looks like a trivial question. It is not. And let's now discuss methods for answering this question. And let's take into account that we often need to classify water in two categories. Surface water, I am making a selection in the page, and the term is self-explaining. Surface water is water that you can see because it's located over the Earth's surface, so rivers, lakes, sometimes ice, because also ice, snow and ice are important water reservoirs. Let me check if there are questions in the chat. I think there is still a person in the waiting room. Yes. Okay. And so surface water and groundwater. You see, surface water or groundwater. And groundwater is available in aquifers. Now, what is the difference when we talk about surface water? What is the difference between river and lakes? Essentially, from a technical point of view, I like to say that the difference is the water velocity. Because in a lake, you have a water flow, but it's almost steady. I mean, it's the velocity of the flow is almost zero. In a river, water is flowing with a higher velocity. And keep in mind, as I already said before, that velocity is important because if water is flowing with a high velocity, it means that there is a high volume involved there. Even if the volume of the lake in static condition is much higher than the volume of the lake that is at a given time it's stored in a river, because the river, the depth of the river is very reduced. So if you take a picture of a river and you estimate the volume of water in that picture, it's negligible compared to the volume of water into a lake, but the water in the river flows. It means that the volumes, the involved volumes, the available volumes of water are maybe much higher than the volume into a lake. So this is the basic difference. Now, groundwater, it's something that it's a bit complicated because you can't see it. You can monitor groundwater through wells or through remote sensing, but it's a difficult monitoring, and it's very hard to provide a very detailed description of how an aquifer works. You don't know the geometry because you can't see it, and sometimes you don't know the velocity of the flow because you cannot observe the velocity of the flow. In a river, you may take a velocity measurements. Into a groundwater aquifer, it's much more complicated. So let's try to understand a little bit more how they work. Here you see a picture of an aquifer. Look at this image, which I put in the screen and I magnify it. So aquifers, first of all, are replenished by infiltration, meaning that you get some rainfall. When it rains, you get some rainfall infiltrating into the ground, and then the water gets stored in aquifers. You see these drops here under the number 3 on the left and on the right. This is rainfall that infiltrates and the yellow layer, it's a permeable layer, while the red layers are impervious. So it means that you cannot have infiltration in the impervious layers, but you can have infiltration of water in the pervious layer, in the permeable layer. So you get water flowing into the ground by following my mouse here. And then it gets stored in the underground, typically between two impervious layers. And then what may happen is that if you dig a well, look at 4, dig a well through, let me say, the impervious layer, and you reach the aquifer, then for the effect of pressure, look at the level here of water into the pervious layer. Look at my mouse and look at the dashed black line. This is the level of water. You see the same level in the left part and the right part of the aquifer. Now, if you look at the well number 4, if you reach with the well the aquifer, water goes up the well, up along the well, and may spring out of the well spontaneously without any pumping. Why? Because the level of water into the aquifer, look at the dashed line, is higher than the level of the ground. This is called an artesian aquifer. These are not very frequent. They are very convenient because, as I said, you can get the water without pumping. Now, let's look at the other well number 6. The well number 6 is located in a place where the ground level is higher than the water level, is higher than the dashed line. So you get a well into a confined aquifer, okay, into a confined aquifer. Because why confined? Because you see there are two impervious layers that are around the aquifer, so it's confined, okay, here. And you get a well into a confined aquifer where you need to pump in order to get the water at the ground level of the number 6. Pumping is a little bit, costly, requires energy, but still, this is water that is readily available. Now, if you look at the right part of the graph and you look at the aquifer, there is a place, number 7, where the aquifer gets to the surface, and then you get a spring. So water after infiltration may naturally emerge in the form of springs. Springs are surface water due to the emergence, in this case, of an aquifer. And in the right part, when the aquifer, you see, is no more confined, because basically the permeable layer, it's not confined here. Look at my mouse. The permeable layer reaches the ground surface. It's not confined. The aquifer not confined is called unconfined aquifer or phreatic aquifer. So the same aquifer may be confined in some places, like you see number 1 here. In this zone, it is confined, and it's unconfined in the right part, number 3. And the unconfined aquifer is also called phreatic aquifer. Everything is written in the web pages, so don't be concerned because everything is explained there. So phreatic, unconfined, and confined aquifer, which may be artesian if water can be extracted without pumping. Okay, so sometimes you listen people saying, I have an artesian well, so you know what it means. It means that in this well you can get water without pumping. Or I have a phreatic well. It means here you don't have any representation of a phreatic well. If you put a well here under number 3, and you get to the depth of the aquifer, then that would be a phreatic well. And the phreatic aquifer is more vulnerable, of course, because if you have pollution over the ground, let's think about a dispersal of oil over the ground, okay? Dispersion of oil, for instance, by a tank. And then if the aquifer is permeable, the oil can infiltrate itself and can reach the aquifer. So the phreatic aquifer is more vulnerable. The confined aquifer is less vulnerable, so the quality of water is generally higher in the confined aquifer. Keep in mind that in general, water in the aquifers is less vulnerable than surface water. It's relatively easy to pollute a river. It's not so easy to pollute an aquifer because it requires some time to the pollution to get to the bottom, to get to infiltrate into and to reach the aquifer. On the other hand, there is to say that once it is polluted, an aquifer is much more difficult to recover. Recovering a river is relatively easier. Recovering an aquifer, it's not so easy. And there is another thing to say, an important difference between surface water and groundwater. The velocity of the flow in the groundwater is much lower than the velocity of the flow into a river, unless you have some karstic areas where you have underground rivers there. In general, water flowing into the soil, the velocity of the flow is much, much lower. And this is, something that you have to take into account because, as I said, it means that you have less water there. And another thing, it takes more time to recharge. So when you use aquifers, you have to be very careful because it may happen that it takes a long time to recharge them. And this is the big question related to water resources management today at the global level. This is the big question. What is the big question? The big question is groundwater use sustainable? It's difficult to reply to this question because for a river, you understand when it's not sustainable. You try to get more water, the river dries up. It's clear that it's not sustainable. And then you stop getting the water and you see back the water into the river. Good. I mean, I can go with trial and error with rivers. Of course, it's better if I avoid the errors, but if I make some mistakes, it's not difficult to recover. For a groundwater, you don't see the water underground. So you try to get the water through the well, and then at a certain point, the well dries up. But if you stop getting water from the well, it may take 100 years before you see water back into the aquifers. And so this is the big question today. How much water is there in my aquifer? And some people think, I am making consultancy activities for water boards, and they think that this is an easy question to answer. Tell me how much water is in the underground of our region. And I say, it's impossible, I can't tell you. And they say, why? Because, I mean, we don't know the geometry, we don't know the porosity, we don't know the geology. We have to make trillions of measurements if we want to get the necessary information. And then we don't know how much water is there, and we don't know how much it takes to recharge. So this is the big question at the global level. There are thousands of scientists working on this, building models, because observations are not enough. So they try to build models. They try to understand how water flows in the underground. We will not see this problem into detail because, this is not a course on groundwater modeling. On the other hand, it's important that you are aware of this. And this is another picture which is more or less, it's representing a different aquifer, but you can see here the unconfined aquifer, also called phreatic, and you see the confined aquifer. You see that the limit in a phreatic aquifer, the surface of separation between the saturated soil and the unsaturated soil is called the water table. So when you listen this term, when you hear this term, water table, you know that it's the water surface in the underground. It's the separation surface between the saturated soil and the unsaturated one, okay? And I would say that for aquifer, that's it. There is a link to a video here, which is extremely interesting. It takes 5 minutes. It's not much. I mean, it's an introductory video, but I suggest you to have a look. And I just click on the link in order to show you the first 30 seconds. And first of all, it's in English, of course, and it explains with subtitles how aquifer work. And let me just take the audio off, and you see that basically it says the same thing that I said, but in 5 minutes and through a video, it's more entertaining, more exciting. So I suggest you to look at it. You see the confining layer, the phreatic aquifer, the unconfined one, and it's very nice. In general, let me go back to the web page. In general, this collection of videos presented here in geoscience videos, it's, I mean, I believe it's extremely interesting. I am using many of these videos in my lectures. And there are videos for many things, climate change and whatever. You see that there is introduction to geoscience, and then the Earth system, and then plate tectonics. This is not interesting for us, but still, it's very nice. And yeah, there are a lot of videos. And also on water, I think, let me go back and go down. I think there is a section which is dedicated to volcanoes here, to water. And let me see. Water on the Earth. You see stream flow and the stream flow width. Where is the water table? What is an aquifer? Our video. Porosity and permeability, resources and climate change, etc. So I suggest you to have a look if you're interested, and just for fun, because it's fun, but it's also an opportunity to learn. And they are, I think, well done. They are objective. They are rigorous, scientific. Okay. So I said that mathematical modeling is not only the solution. And in any case, also, in order to set up a mathematical model, we need monitoring to answer to the question, how much water is there? So monitoring is essential in water resources management, both for surface water and groundwater. And there are traditional monitoring techniques. Usually they are local, meaning that a traditional monitoring technique, for instance, is the rain gauge. It's an instrument, a tool that allows you to measure rainfall, but it's local, it's point rainfall. Another traditional tool for monitoring is the water velocity meter, which is called in Italian mulinello. It's a kind of rotating spin, which if it's put into the water, allows you to measure water velocity. Another local monitoring instrument is the thermometer or the anemometer, measuring wind velocity. These local monitorings are very useful. On the other hand, give you a local representation. And we are facing now the problem of providing regional and global descriptions for the reasons of coping with sustainability. So water is not a local problem, it's a global problem. And then if you use local information, which is, I mean, very important, very useful, on the other hand, you have the problem of extending in space this information. And so recently, there has been a consistent effort towards remote sensing and through Earth observation by using remote sensing. Earth observation includes water observation. And therefore, we had an increase, a sharp increase in the past 20 years of spatially distributed, spatially extended information through Earth observation. How is Earth observation obtained? How is remote sensing obtained? There are several monitoring, remote monitoring instruments that can be used. And the most important are the satellites. The satellites, it's what Google Earth uses. And I think you are very familiar with Google Earth and the incredible value of Google Earth, because it allows you to visit any place in the globe and to get a glance, but a very detailed glance of the topography there, the vegetation cover, the urbanization, a lot of information that are very useful for water resources management. And besides satellites, we can use other monitoring instruments like the weather radar. So we can use radars, and we can use also other advanced monitoring systems, like for instance, the intensity of the cell phone signals that allow us to measure humidity, rainfall, etc. Monitoring can be at a single time, and therefore you get a snapshot. And this is what we call usually discrete time monitoring, or maybe continuous in time. And for instance, satellites give you time continuous information. And it is, of course, continuous monitoring is definitely more useful because it gives a comprehensive picture of time variability. When we get these observations, which may be discrete or continuous in time, what we obtain is what we call a time series. What is a time series? It's a series of observation of the considered variable listed in chronological order. And examples of variables that are interesting for us are the river discharge. What is the river discharge? Keep in mind this definition. It is extremely important. You cannot talk about water resources management if you don't know a couple of definitions that now I am introducing. Now, river discharge, it's the volumetric flow rate of water that flows through a given cross section of the river at a given time. So you need to refer to a cross section. We will see in a moment what a cross section is. But let's say you need to refer to a river location and you need to refer to a given time. The river flow or volumetric flow rate or river discharge is the amount of volume that flows through the cross section per unit time, or in more rigorous words, the volumetric flow rate of water that flows through a given cross section at a given time. When I say flow rate, I mean water volume per unit time. So if I ask you at the exam the definition, what is river discharge, you may say this definition here, or if you prefer, you can say it's the amount of volume that flows through a given river cross section per unit time. I hope it's clear. And let me see if I have some questions in the chat. It seems not, but let me check if I always see a student that is in the waiting room and I don't understand why. Okay. Okay, now another example of time series may be the groundwater level, rainfall intensity at a given location, temperature at a given location. And I still have to define what is a river cross section. Now, somewhere it is defined. Let me see if I have the definition here. I think it is defined in the next lecture, but I want to anticipate it now. What is a river cross section? When you refer to a given river location, I mean, you travel along a river, at a certain point, you stop, you stand up, and you look at the river. You are at a given river location. You can identify a dominant direction of water velocity, which is downstream. Okay, so let's identify this dominant velocity vector. And then let's cut the river with a plane that is perpendicular to the dominant velocity vector. So I cut the river perpendicular to the water flow, okay? And then by cutting the river, I get a geometry of what we call a river cross section. Let me see if I still have, yes. Let me make a picture here. Okay, so I need to share the screen, but I think I can do like this. Yeah, perfect. So let's suppose that you are along a river. 1 second, I take a blue color. Okay, good. Let's suppose that you are along a river, okay? And at a certain point, you stop to a given location. Let's suppose here. Okay, let's identify the main velocity vector in this point of the river. Let's suppose that it is this one. Okay, this is V. Good. Now let's cut the river with this plane. So if I look from above, I cut the river here with this plane. The figure that I obtain is something like this. Okay, something like this. And I can indicate here the water level, like here. Okay, this is precisely the cross section. The important thing is that the river flow comes out from this cross section perpendicularly and comes through me, through you that you look at the screen. So the cross section is depicted by looking from downstream to upstream. Good. The definition is provided in the next lecture. The time span during which the time series was observed is termed observation period. Okay. And the longer the observation period, the higher the reliability of the information. This is quite trivial. Okay. Now, let me give you an example of a time series which is displayed in a quite unusual manner. This is a creation of mine, so I take the responsibility. If you don't understand this figure, it's my fault. So this is the Po River at Ponte Lagoscuro, and it's Ponte Lagoscuro, it's conventionally the closure cross section of the Po River. What does it mean, closure? Means that at Ponte Lagoscuro, conventionally, it's located the end of the Po River before getting into the delta. This time series is daily. So here you can see the daily flows at Ponte Lagoscuro from 1920 to 2009. Here there is a mistake that I never noticed. It's not 2099, but 2009. So sorry for that. Now, how it is represented? It is represented in 3D. In the vertical axis, there is the flow. In the two horizontal axes, you see the years and the days. So this allows you to understand the intra-year variability and the inter-year variability. So if you travel along the year, along the days, you see the seasonality. So the Po River is characterized by a dry period during summer and two high flow periods in late spring and the fall season. And you see that seasonality. If you travel along the years, you see the variability, the inter-year variability, which is less, let's say, less intuitive than seasonality. Seasonality, we all know what is, but from year to year, we are tempted to assume that there are no big changes. Instead, if we look at this figure, we see that there is variability also when traveling through the years. And in particular, there are some high flow periods that appear and then disappear, and there are many droughts. And what is interesting to say, if you look at the summer period, you see that there is a red spot around 1940, 1950. This is a well-known long drought that occurred in Italy at that time. It was a cycle, a long-term cycle. And this is something that we have to take into account when talking about river flow, weather, rainfall. We have to be aware that sometimes we experience long-term cycles. So for instance, droughts that can last for 10 years for whatever reason. We don't know the reason. And we know the reason of seasonal variations, but we don't know really the physical reasons. We don't know why sometimes very long-term cycles occur, and sometimes there are flood-rich periods as well. The last thing to say is that this time series is smoothed, because in order to understand this macroscopical behaviors of variability, I needed to smooth it. Okay, I think we can stop here for this with this premise, and then we have to turn to water resources assessment. Okay, just before I move to the next lecture, I want to make sure that you don't have any question, any comment on this. Let me check on the chat. Good, I don't see anything. So let me go back to our list of lectures while I keep the chat monitored. We have about half an hour more to go. Let me just give me 30 seconds. I take off my sweater. Spring is coming, but it seems that from tomorrow we are getting back to some cold weather. We will see. Okay, so nothing is on the chat. I'm just curious. I'm looking at the trial that I made with the form. Fine. So 10 students voted, and 90% say that my velocity is fine. Okay, let's hope that you are not too lenient with me. Now, let me go to assessing water resources availability. So I said that we have two options: measurements or mathematical modeling, which we can blend together. So these two options are discussed here in two lectures: inductive methods and deductive methods. So mathematical modeling is included in the deductive methods, and getting information directly from observations is included in the inductive methods. Let's start with the inductive methods. Okay, give me 1 second. I wanna just check. Okay, perfect. Okay, so inductive methods. Now, our question is now assessment of water resources availability, and it is a classical problem. I mean, it has been dealt with by humans since the antiquity. And keep in mind, for instance, that we have the nice examples of the ancient Egyptians. And as you know, they took their wealth, they took their support for water and fertilization for food production from the Nile River. And their wealth was connected to the floods of the Nile River. Because when flooding, the Nile River was distributing a very fertile mud over the land. So they were much interested in trying to know better the dynamic of the Nile River flooding. And they built the Nilometer, which is a measuring instrument that allowed them to understand better the dynamics of the Nile River flows. And it's interesting, I think there is a link here, but let me open another web page and let me show you a picture of the Nilometer. It's located at El Cairo. And let's open this Wikipedia page. And you see it's the measuring instrument. It's located here. This is a measuring instrument. And basically, this is a column that is it's wetted by the Nile River. So the Nile River water is allowed to come up from this big well. And let me check, because again there is a student in the waiting room. Okay. And so water is allowed to come up from this well, and water wets the column. And every year, because they took a measurement every year, an annual measurement, they went down along these stairs to see where was the water sign located. And then they recorded the water levels in this scale, which is placed on the walls of this well, which is was their way to keep this recording. And here is an external picture of the Nilometer. And so you see the Nile River that goes through these galleries here. Where is my mouse located? Water goes in, and then there is inside this structure the column that I showed you before. And they continued the measurement for 600 years. And this is one of the most of the oldest time series that we have. It has been extremely studied for understanding something about natural climate variability. Okay, and however, our relevant challenge is lack of data. Let me show, because I have a PowerPoint presentation for this. So I think, okay, here it is. So let me use it. And okay. And the problem, as I said, it's lack of data. And this is lack of data is particularly concerning for groundwater. And this is a widespread problem. Lack of data is a well-known problem. And therefore, in hydrology, several methods have been set up in order to resolve this problem. And it's interesting to have a look at the history of water resource systems. If you go back to the previous web page, there is a link here to a review, which I found very interesting, which it's a brief history of urban water supply in antiquity. And this is a published paper. And it is interesting because it shows that this problem of monitoring and assessing water resources availability is indeed an old problem. Now, keep in mind that why the problem is old, because water is essentially needed for food production. This was the problem in the ancient times. Usually in the ancient times, people didn't have problems for securing water for civil use. They didn't have this problem because they tried to locate where water was available. And water for civil use, it's not a problem, first because it's priority. So the modern regulation, the law in force in all countries, set a priority for water for civil use. It has the priority over water for irrigation. And second, I think we already discussed that much of the water demands are related to agriculture. The global percentage of water consumption, it's dominated by the agricultural demand, 70% of the global. And this split between 70% to agriculture and the remaining 30%, it's about 25% to industrial production and 5% only to water for civil use. This split, 70 agriculture, 25 industry, 5 civil use. This split is also echoed in Italy. In Italy, we have the same distribution more or less. So you understand that the big problem is water for food. Okay, now this slide basically says what we already discussed. What is a cross river section, and what is the inductive of deductive method, and the difference between river and lakes, velocity of the flow essentially. So I think I can easily move forward. Now, let's focus now on a specific problem, one first specific problem, which is the inductive assessment through data of water resources availability at a given cross river section. And this is a classical problem. Why it's classical? Because usually the first solution that we human adopt and always adopted to get water is to get water where it's easily available, a river. A river is a water body where we can take water directly. We can even drink directly if it's clean. It's delivering a lot of water because of its high velocity. The water is frequently replenished, and there is a rapid exchange time. What does it mean? It means that if water flows quickly, the quality is higher with respect to water in lakes, where the residence time is much, much higher. And therefore, it was a classical solution to settle down, to build cities close to rivers and taking water directly from the river. At the beginning, it was also very easy because the river was not polluted. And then some problems came with water quality, but it was a later problem. And at the beginning, I mean, wells were very infrequently used, only during the dry season, and only in very specific locations where people, for some reason, needed to settle down, even if surface water was not available. Now, how can we resolve this relatively simple problem of estimating water resources availability in a cross river section? Do you have any questions? I just would like to keep you stimulated to ask questions if you have any doubt, and to let me know if there are some problems related to my teaching. Now, teaching is getting a little bit more technical for a while. So if you don't understand, I am too quick, just let me know. So what is our problem here? How much water is available in a given cross section? We need measurements. We need measurements of water flow. We already know what is water flow. So it's or river discharge. We already defined it. Now we have to look, if we want to solve our problem, for measurement of river discharge in the place we are interested to get water. Usually we are interested in getting water from a river at a given location, and we want to know how much water we can take. This is our problem. It's our problem because, water, once that we build an infrastructure to get it, we are interested in, of course, in getting as much as water as possible within a sustainable framework. So we are interested, of course, in getting much water, but we don't want to make unsustainable actions. So the question is a bit complicated. Now, as I said, you have to look for observations. Let's assume for now that you have them. So we will deal later on with the problem of lack of data. Now, let's suppose that you have this historical time series of observation of river flows listed in chronological order. Okay. Now, the way we resolve the problem then is through the estimation of the flow duration curve, also called with the acronym FDC. I think some of you already know what is the flow duration curve. So so we make a small break. Let me try again with another form. And let me see. Okay. Okay. So let me put the question. Okay. Anonymous reply. Okay. Now you have a poll in the chat. Please vote. So while I continue talking, and I just would like to know how many of you already know about it, because in any case, I will make a recap. So I will just show you. But of course, if most of you already know it, I would say that I can go more quickly. Okay, because I think you already had another course dealing with it, another subject. Yeah, almost all of you. Yeah, okay, this is great. Okay. Keep in mind that this will be a usual question at the exam. Everything is explained in my lecture. And so I think that for those of you who already know it, it's okay, but please make sure that you have all the information available, that the information that is reported on my webpage, okay? And for those of you who don't know about it, just keep in mind that I will be quite quick because I don't want to spend much time on a topic that most of you already know. On the other hand, on my web pages there is everything, and if you wanna get more details, you may refer to me, or you may look at my lectures of the previous years of the same subject, sustainable design of water resource systems, and you will find there more detailed lectures. Now, the flow duration curve starts from an hydrograph. What is an hydrograph? It's a picture presenting the progress of river flow along time. And what does the flow duration curve depict? And just 1 second, because I got a message. Okay. Okay, good. What is the flow duration curve depicting? It depicts the percentage of time, also called duration, over a given observation period, which is typically maybe 1 year, maybe 10 years. It depicts the percentage of time over a given observation period during which a given stream flow is equaled or exceeded. So this is the definition that you have to repeat to me at the exam if I ask you what is a flow duration curve. The typical question is, what is a flow duration curve and how you estimate it, how we can estimate it. So if you have the hydrograph, look, and you refer to a given stream flow, for instance, the stream flow that is given by the position of the blue line, okay? So here in the left graph, you have a picture of stream flow against time, the hydrograph. Stream flow is a synonym of river flow, of river discharge, etc. Now, given that we have to identify the percentage of time over a given observation period during which a given stream flow, the blue one, is equaled or exceeded, it's clear that if we compute the ratio between the sum of B plus C for the blue stream flow, the sum of B plus C divided by the total length of the observation period D, this ratio B plus C divided by D is the duration, the percentage of time over a given observation period D during which the blue stream flow was equaled or exceeded. The same for the stream flow A in red, okay? And the flow duration curve is reported in the right graph. You see B plus C, A. And in order to get the duration expressed in percentage, this B plus C and A should be divided by D, as I said. Keep in mind that the duration may be expressed in percentage of time or may be expressed in terms of time. So we may say that a given stream flow has a duration of 10%, which means that, or we may say that a given stream flow has a duration of 36 days in a year, which is 10%. Now, I think this graph is clear in explaining how the flow duration curve is estimated. From a practical point of view, we will make an exercise. So I suggest that we don't focus here with much details on the practical estimation, because we will make an exercise, and I would say that it could be next week on, I don't know if it is on Monday or Thursday. It doesn't make a difference for you because I would say on Monday, okay? I will take 1.5 hours on Monday to make this exercise. Now, I just want to tell you that something that you probably will not understand at this stage, but I will give you later on the means to understand what I'm saying. From a statistical viewpoint, the flow duration curve is the cumulative probability distribution of the stream flow. So it's equivalent, fully equivalent. So those of you who know about what is a cumulative probability distribution may understand me. And okay, very good. I'm looking at the result of the pool, and then I will start another one to check how many of you know the concept of cumulative probability distribution or density probability distribution. This is another thing that we need to know. Now, keep in mind that the explanation, so probability means frequency. So when I say that an event have a high probability, it means that has a high frequency. Probability in technical terms can be understood as a synonym of frequency. And therefore, you can understand the similarity with the flow duration curve. The percentage of time is a frequency. So both probability and the flow duration curve are tightly related to the frequency. So you can understand why they are also related to each other, probability and flow duration curve. And this is what this slide says. But again, if you have some doubts of what I'm saying, just be patient a little bit, because we will explore this relationship between flow duration curve and probability with more detail. Now, this is how the flow duration curve can be estimated. And again, we will make the exercise on this. Just keep in mind this slide, read it, because you will be able to more rapidly follow me when we will make the exercise. And just let me say that we have two methods for estimating the flow duration curve, and we will apply both of them. And let me make clear the difference between the two. So what you see here is the way to estimate the first method, the flow duration curve, by putting all the observations together. So let me make an example. The example is a river for which we have 10 years of daily observations. And we want to estimate the flow duration curve over the period of 1 year. So we have 10 years of observations, and we want to estimate the percentage of time during a year when a certain flow is equaled or exceeded. So again, you have two options. The first one is what you see here. let me read the numbered items. Pool 1, pool all observed stream flows in one sample. So you have 10 years. It means that you have 10 times 365 numbers. Actually, you have a bit more because there are the leap years, but let's forget about the leap years. So you have 3,650 observations. You pool them together, and then you rank this pool of observations in descending order, or okay, here there is in ascending. It doesn't make a difference. Let's say that you rank them from the highest to the lowest. This is more. I would say that in descending order is better than in ascending. Okay. So let's assume that we rank them in descending order. Then we have to identify the position of each observation in the ordered sample. So let's suppose that the sample is ordered in descending order. The highest value of stream flow is in the first position. The second highest is in the second position, and so forth. The lowest value is in the position number 3,650. Perfect. Now we have to plot each order observation in a graph versus its position in relative or absolute terms, meaning in terms of percentage or in terms of duration, absolute duration. That's it. We got the flow duration curve because the highest value was equaled or exceeded only once. So if I plot the highest value against its position, I already get the position in the flow duration curve of the highest value. So by plotting each value against its position, I get everything I want. This is the first method. Now, let me instead focus on an alternative. If I have 10 years of data, instead of pooling all the observations together, I can split the data in 10 parts, one group for each year. So I put the data of the first year together, the data of the second year together, etc. And then for each year, I estimate the flow duration curve according to the procedure that I explained in the previous slide. What I obtain is 10 flow duration curves. And look at this picture. In this picture, you have many flow duration curves in light gray plotted together. Forget about the blue lines for now. And focus your attention on the gray thin lines. These are many flow duration curves. And then I can compute the average, the red line, or the median. In this case, it's the median, but let's say the average, which is more understandable. And this is an alternative. I mean, with the first method, you pooled all the data together. With the second method, you pool all the flow duration curve together and compute the average. What is the advantage with the second method? Look at this picture. Besides an estimation of the average of the flow duration curve, you also have an estimate of year-to-year variability. The spread of the gray thin lines gives to you what is the spread of the flow duration curve around the average. And this is extremely important because it gives to you an estimate of variability, of uncertainty. In water resources management, we are not just interested in the average water that we have available. We also need an estimate of variability, because variability means that in 1 year we may have much more than the average and we are happy, but variability also implies that in some years we may have much less than the average and we are unhappy. So the average is not really a comprehensive statistics for water resources. We need an estimate of variability. And in fact, here you see that we also estimated the blue lines. What are the blue lines? The blue lines encompass for each duration, they encompass 90% of the variability. When you see P equal 0.05 means probability 5%, P 0.95 means probability 95%. The interval of probability between 95% and 5% is precisely 90%, and this gives an estimate of the variability. This is what is done here. At this stage, you may say, so if this method is more convenient because it gives an estimate of variability, why we don't use it forever? Because the previous method, which doesn't give you an estimate of variability, it gives to you a representation of the flow duration curve, which is more detailed. And I will explain to you what it means when we will make the practical exercise. And just keep in mind that a usual question at the exam is, what is a flow duration curve? How you estimate it? And you should be able to explain one method and the second method. And again, if you didn't understand so far, don't worry, because on Monday, we will make it in R, and I'm sure you will understand. And another additional question may be, what are advantages and disadvantages of these two methods? And the advantage of the second method, I already explained to you, estimate of variability. The advantage of the first method, which I only mentioned, more detailed representation of the average, more detailed representation of the average, I will explain to you on Monday with more detail what it means. And I think it's much better if I do it on Monday because, you know, when you work with numbers, you understand much better than working in theory. Let me see what is the next slide. Yeah, I think we can postpone this discussion to Monday morning. So Monday, let's say that about 1 hour and a half, which means 45 plus 20 minutes, I will hopefully I will move forward with the lectures, and then I will dedicate the remaining time to the exercise. By the way, the exercise is already on my website. Now, I think I can share my screen, and 1 second, and I put a last question for you. Meanwhile, if you have any question, please use the chat while I prepare the form. Okay, 1 second. The question I want to ask you, it is this one. Okay. And it's still anonymous, you know. Give me 30 seconds. Okay, anonymous, save, send. Okay, you see in the chat, you can ask questions or you can, and meanwhile, please vote. I think I need to make a recap of probability then, because probability for us is extremely important. So I think I need to make a recap. Don't worry, it will be fun. Do you have any question on the chat? Okay, so I think that if you have some time, you can. You still have, let's say, 1 minute if you wanna put any question. Otherwise, I hope you enjoyed it. It is for me. These are really fascinating topics. I mean, to try to understand how much water we can take from a river. I mean, it's something that it's like an historical challenge for humans. So for me, it's really fascinating, but of course it also depends. The fascination also depends on the ability of the teacher. So I hope that you could find it fascinating as well. Okay, and I think we can say goodbye. Enjoy your weekend, and let's meet on Monday at 9:15. I will start. Thank you. Thank you very much.
See you next week.
Okay. Thank you. Bye-bye.
Bye.